learning.
What is deep learning? Yeah. So we're trying to learn from all this data. We're trying to learn what's important. What's it telling us? So you've got data. You've got some inputs for which you know the right outputs. The question is, can you see the pattern there? Can you figure out a way for a new input, which we haven't seen, to get to understand what the output will be from that new input? So we've got a million inputs with their outputs. So we're trying to create some pattern, some rule that'll take those inputs, those million training inputs, which we know about, to the correct million outputs. And this idea of a neural net is part of the structure of our new way to create a rule. We're looking for a rule that will take these training inputs to the known outputs. And then we're going to use that rule on new inputs that we don't know the output and see what comes.
Linear algebra is a big part of defining or finding that rule.
That's right. Linear algebra is a big part. Not all the part. People were leaning on matrices. That's good, still do. Linear is something special. It's all about straight lines and flat planes. And data isn't quite like that. You know, it's more complicated. So you got to introduce some complication. So you have to have some function that's not a straight line. And it turned out, nonlinear, not linear. And it turned out that it was enough to use the function that's one straight line and then a different one, halfway. So piecewise linear.
Piecewise linear.
One piece has one slope, the other piece has the second slope.
Yeah.
And so that getting that nonlinear, simple nonlinearity in blew the problem open.
That little piece makes it sufficiently complicated to make things interesting.
Exactly, because you're going to use that piece over and over a million times. So it has a fold in the graph. The graph is two pieces, but when you fold something a million times, you've got a pretty complicated function that's pretty realistic.
So that's the thing about neural networks.